Welcome! In this session, we'll explore an exciting graph problem from LeetCode, problem number 1203, sort items by groups respecting dependencies. This problem challenges us to sort items while adhering to both group constraints and dependency relationships, making it a fascinating mix of graph theory and topological sorting. Let's dive in and unravel the solution step by step. In this problem, we are tasked with sorting n items where each item may belong to one of m groups, or to no group at all. The grouping information is provided in the group array, where group I tells us which group the ith item belongs to. If group I equals -1, it means the item does not belong to any group. Additionally, we are given a before items array, where before items I lists all the items that must be completed before the ith item can be started. The goal is to return a valid order of items such that items within the same group remain contiguous, and all dependencies specified in before items are respected. If there are multiple valid solutions, we can return any of them, but if it's impossible to satisfy the conditions, we should return an empty list. The constraints for n and m provide the problem scale, with n being up to 30,000 and m up to n. The before items array is a key part of this problem. It specifies dependencies between items, where each entry before items I lists the items that must come before the ith item. The output of our function should be a list of integers representing a valid sorted order of items. If it's impossible to satisfy the constraints, we return an empty list. For example, consider the input with 8 items in 2 groups. The group array specifies the group membership of each item, while the before items array defines the dependencies. A valid output for this input might be 6, 3, 4, 1, 5, 2, 0, 7, which satisfies both the group contiguity and dependency conditions. Breaking down the first example, we see that items are divided into groups as follows. Group 0 includes items 1 and 2, Group 1 includes items 3 and 4, Group 2 includes items 5 and 6, and items 0 and 7 do not belong to any group. A valid order like 6, 3, 4, 1, 5, 2, 0, 7 ensures that dependencies such as item 6 being completed before items 3 and 4 are respected, while keeping items within the same group contiguous. In contrast, the second example demonstrates an unsolvable scenario. Here, the dependencies create a situation where it's impossible to arrange the items in a valid order, so the output is an empty list. Looking at another example, consider a case with 5 items divided into 5 groups. The group array specifies the group assignments, and the before items array defines the dependencies. In this scenario, the output 2, 3, 0, 1, 4 is a valid solution, as it respects both the dependencies and the grouping constraints. For instance, item 3 comes after item 2, and items in the same group remain contiguous. This illustrates how the problem requires careful handling of both topological sorting and group-based constraints to arrive at a valid solution. Now, turning to the constraints, the problem ensures that the number of items, n, is between 1 and 30,000, while the number of groups, m, ranges from 0 to n. The group array has a length of n, and each value in group is either -1 or a valid group index. Similarly, before items has a length of n, and each sublist contains distinct integers between 0 and n1. These constraints ensure that the problem is computationally feasible while allowing for a wide variety of input configurations. Some critical edge cases include scenarios where all items are ungrouped, where there are cyclic dependencies, or where there are no dependencies at all, requiring careful handling in the solution logic. Additional edge cases include when there is only a single item, in which case the output is simply 0, since there are no dependencies or grouping concerns. Another case involves disconnected groups with no dependencies between them. In such cases, any order that respects the contiguity of items within each group is valid. These edge cases highlight the importance of designing a robust solution that accounts for the full range of input possibilities while ensuring correctness and efficiency. To tackle problem number 1203, we need to address 2 levels of constraints: intergroup dependencies, which define how groups depend on each other, and intragroup dependencies, which are the relationships between items within the same group. This makes it clear that we need to use topological sorting combined with graph traversal techniques. Now, one approach we could consider is the brute force method. The intuition here is to manually resolve all dependencies by first sorting the items, then sorting the groups based on those item dependencies. However, this method has significant challenges. It struggles with scalability because repeatedly checking dependencies becomes inefficient as the input size grows. Additionally, cycles in dependencies could make this approach unreliable. While the brute force method is conceptually simple, it becomes computationally infeasible when the number of items in groups increases, making it unsuitable for larger inputs. A more efficient approach involves using an optimized topological sort with multiple graphs. Here, we represent the problem with a two-layer graph structure. One graph handles the group-level dependencies, while the other focuses on the item-level dependencies within each group. The implementation involves several steps. First, standalone items, or those not assigned to any group, are treated as virtual groups. Then, we construct a directed graph for the groups based on the given dependencies and another directed graph for items within each group. Using these graphs, we perform topological sorting. Groups are sorted first using algorithms like cons or DFS-based topological sort. After that, items within each group are sorted independently. Finally, we merge the sorted items by following the order of the sorted groups. This method is efficient, with a time complexity of O, n plus e, where n is the total number of items and e is the total number of dependencies. It ensures that all constraints are respected, but careful implementation is needed to maintain the two graphs and their relationships. Another possible approach is to flatten the problem by treating all items as independent nodes in a single graph and performing a single topological sort. Group constraints are resolved later during the merge step. While this method simplifies the graph structure, it introduces new challenges. It becomes less modular, making the solution harder to debug and maintain. Additionally, resolving group-level constraints during the merging process can be prone to errors. Although the time complexity is comparable to the optimized approach with multiple graphs, this method lacks the structure and clarity provided by separating the problem into distinct layers. Because of these reasons, it's more difficult to reason about and implement correctly, making it less preferable than the two-graph approach. The key insight that simplifies this problem is treating standalone items as virtual groups. This makes the graph construction process more intuitive and allows us to map the two levels of constraints directly to a two-layer graph structure. This modularity is what makes the chosen strategy particularly effective. Alternatives like the brute force method fail to scale, and the single graph approach sacrifices modularity, increasing the likelihood of implementation errors. While the two-graph approach does require additional memory to store the separate directed acyclic graphs, the trade-off is minimal compared to the benefits of clarity and correctness. Ultimately, this strategy strikes the right balance between efficiency, scalability, and maintainability, making it the optimal approach to solve the problem while adhering to all constraints. In this problem, we need to sort a collection of items while respecting two types of constraints. First, there are intergroup dependencies, which define dependencies between different groups of items. Second, there are intragroup dependencies, which define dependencies among items within the same group. The challenge is to return a valid sorting order that satisfies both constraints or determine if no such order exists. To tackle this, we use a two-level approach with topological sorting. First, we sort the groups themselves based on intergroup dependencies, and then we sort the items within each group based on intragroup dependencies. The initial step in the process is to parse the input and set up the necessary data structures. This includes extracting the total number of items in groups, assigning unique groups to items that don't belong to any group, and constructing graphs for group and item dependencies. Additionally, we create in-degree arrays to track incoming edges for both groups and individual items, which will help facilitate topological sorting later on. The next step is to build the dependency graphs. For each item, we check its dependencies listed in the before items array. If an item has a dependency that belongs to a different group, we add a directed edge from the dependent group to the items group in the group dependency graph and increment the in-degree of the items group. On the other hand, if the dependency is within the same group, we add a directed edge between the items themselves in the item dependency graph and increment the in-degree of the dependent item. Once the group dependency graph is built, we perform a topological sort on it using Kahn's algorithm. This involves processing nodes with an in-degree of 0 and iteratively removing their outgoing edges while updating the in-degrees of their neighbors. If any cycle is detected, meaning not all groups can be processed, we immediately return an empty array because the sorting is impossible. After sorting the groups, we perform a topological sort on the items within each group independently. For each group, we gather all the items that belong to it, then use Kahn's algorithm again to sort these items based on their intragroup dependencies. If a cycle is detected in any of these item graphs, we know that it's impossible to resolve the dependencies, and we return an empty array. Once the sorting for all groups and their items is complete, we proceed to combine the results. The final order of items is determined by the topological order of the groups. For each group in this order, we append the sorted items from that group to the result list. This ensures that both intergroup and intragroup dependencies are respected. If all topological sorts succeed, we return this combined list as the final sorted order. Otherwise, if any sort fails, we return an empty array. This approach is based on several key insights. First, treating groups as single metanodes simplifies the problem by isolating intergroup dependencies from intragroup constraints. This separation allows us to tackle each level of sorting independently. Second, topological sorting is inherently cycle-sensitive, meaning that if a cycle exists in either the group or item dependency graph, sorting becomes impossible, and we can terminate early. Third, the algorithm is highly scalable, with its complexity dominated by graph construction and traversal. This results in an overall time complexity of O, V plus E, where V is the total number of nodes across both graphs, and E is the total number of edges. To achieve this efficiency, we rely on data structures such as adjacency lists for representing graphs, in-degree arrays for tracking dependencies, queues for BFS-based sorting, and result arrays for storing the final sorted order of groups and items. When implementing this algorithm, it's important to address several edge cases. For disconnected graphs, we ensure that all groups and items are included in the result, even if they have no dependencies. For items without an assigned group, we dynamically assign them to unique groups during input parsing to maintain consistency. Cycles in either the group or item graphs must be detected early, and we return an empty array immediately in such cases. Additionally, empty input should be handled gracefully by returning an empty array as the result. To further optimize the algorithm, we can construct both the group and item dependency graphs in a single pass through the before items array. Incremental group assignment during input parsing helps reduce overhead, and early termination upon detecting a cycle improves efficiency. With careful management of graph construction and topological sorting, this approach ensures both correctness and optimal performance in solving the problem. To solve the problem, we start by addressing items that don't belong to any group. These are represented by a group ID of -1. For such items, we assign them unique group IDs starting from the current count of groups, M, and increment the group count as we go. This ensures every item is part of a valid group. Next, we build the core data structures for our solution, adjacency lists and in-degree counts. The adjacency lists for items and groups, along with their in-degrees, will allow us to process dependencies efficiently. For every item, we check its dependencies in before items. If the dependency is within the same group, we update the item graph and its in-degree. However, if it's an intergroup dependency, we update the group graph and the group in-degree. This setup lays the foundation for topological sorting, which we'll use to resolve the ordering of both items and groups. The next step is implementing the topological sort. We define a helper function, topo_sort, which takes a graph, an in-degree list, and the items to sort. Using a queue, we process nodes with 0 in-degree first, adding them to the result list and reducing the in-degree of their neighbors. If a neighbor's in-degree becomes 0, it's added to the queue. This continues until the queue is empty. If the result list doesn't contain all items, it means there's a cycle, and we return an empty list. We then use this function to sort the groups first. If the group topological sort fails, we return an empty result since the dependencies are invalid. Similarly, we sort the items within their respective groups. If the item topological sort fails, we again return an empty result. After sorting the items, we organize them by their groups, creating a mapping of groups to the list of items they contain, based on the sorted order. Finally, we construct the overall result by iterating through the sorted order of groups. For each group, we append the items in that group, following the order determined in the previous step. This ensures that both intergroup and intragroup dependencies are respected in the final order. Once all groups have been processed, the result list contains the correctly sorted items. This is returned as the solution to the problem. By combining topological sorting with dependency graph analysis, we effectively handle both the item level and group level constraints to produce the desired ordering. To start solving this problem, we first handle the case where some items do not belong to any group by assigning unique group IDs to these items. This ensures that every item is assigned to a group, either explicitly or by creating a new group for them. Next, we need to build the adjacency lists and in-degree counts for both items and groups. The adjacency lists will help us represent dependencies, while the in-degree counts will allow us to track how many prerequisites each item or group has. We initialize empty adjacency lists for all items and groups and set up arrays to store their respective in-degrees. Then, as we iterate through each item, we construct the item graph and group graph by checking the dependencies specified in the input. If an item depends on another item within the same group, we update the item graph and its in-degree count. However, if the dependency crosses group boundaries, we also update the group graph and its in-degree count accordingly. Now, with the graphs and in-degree counts prepared, the next step is to perform topological sorting on the group graph. This determines the order in which the groups can be processed while respecting intergroup dependencies. If the topological sort fails, which happens when there's a cycle in the group graph, we return an empty list, as no valid ordering is possible. Similarly, we perform a topological sort on the item graph to determine the order of items within their respective groups. Again, if a cycle is detected in the item graph, we return an empty list. Once we have the topologically sorted order of items, we group these items by their respective group IDs. Using a hash map, we map each group ID to a list of items belonging to that group. This ensures that we can efficiently retrieve the list of items for any group in the next step. With the items organized by groups, the final task is to build the result in the correct order. We use the topological order of groups obtained earlier to retrieve items group by group. For each group in the sorted order, we add all of its items to the result list. This ensures that the intergroup and intragroup dependencies are both respected in the final output. Finally, we return the result list, which contains all items in a valid order that satisfies the given dependency constraints. This completes the main function, and now we turn to the helper method for topological sorting. The toposort method works by using a queue to perform a breadth-first traversal of the graph. Initially, we add all nodes with an in-degree of 0 to the queue, as these nodes do not depend on any other nodes and can be processed first. As we process each node, we add it to the result list and reduce the in-degree of its neighbors. If any neighbor's in-degree becomes 0, it is added to the queue, making it eligible for processing. This continues until the queue is empty. At the end, if the number of nodes in the result matches the size of the graph is acyclic, and we return the result. Otherwise, a cycle exists, and we return an empty list to indicate that topological sorting is not possible. In the first example, we have 6 items, and no predefined groups since all values in the group array are -1. The task begins by assigning unique group IDs to each item, starting from 0. This results in each item being placed in its own group, and the total number of groups becomes 6. Next, we build the item and group dependency graphs based on the before items array. Here, the item dependencies are sequential, forming a chain from 0 to 5, and because each item is in its own group, the group dependencies mirror the item dependencies. We then calculate the in-degrees for both items and groups, which show how many dependencies each node has. Finally, we perform a topological sort on both the item graph and the group graph. Since there are no cycles, the sorted order for both items and groups is straightforward, 0 through 5. Now that we have the topological order of groups and items, the next step is to group items by their respective groups. Here, because each item is in its own unique group, the mapping of groups to items simply places each item in its corresponding group. Finally, we assemble the result based on the group order. Since the group order is already sorted as 0 through 5, the final output for this example is the list of items in the same order, 0, 1, 2, 3, 4, 5. This demonstrates a simple case where there are no shared groups or complex dependencies. In the second example, some items already belong to shared groups, while others are ungrouped. First, we assign unique group IDs to the ungrouped items, updating the group array and increasing the total number of groups to 4. Next, we build the item and group graphs. The item graph is created based on the before items array, showing the dependencies between items. For the group graph, we analyze intergroup dependencies by examining the group relationships implied by their item dependencies. With these graphs constructed, we calculate indegrees for both items and groups. Afterward, we perform topological sorting on the group graph, resulting in a group order of 0, 1, 2, 3. Similarly, we topologically sort the items, creating an item order of 0, 1, 2, 3, 4, 5. Finally, we group items by their respective groups and construct the final result based on the group order. The output for this example is also 0, 1, 2, 3, 4, 5. In the third example, we encounter a case with a cyclic dependency, which means no valid ordering is possible. All items belong to the same group, so no changes are made to the group assignments. We then construct the item and group graphs based on the before items array. Here, the item dependencies form a cycle: 0 depends on 1, 1 depends on 2, and 2 depends back on 0. This cycle is reflected in the group graph as a self-loop for group 0. The presence of cycles is evident when attempting a topological sort, as it fails due to the circular dependencies. Since neither the groups nor the items can be sorted, the output for this example is an empty list. This highlights the importance of having a valid acyclic graph for dependencies to determine a feasible order. Here, we start analyzing the time complexity of the algorithm by breaking it into individual steps. First, we assign unique group IDs to items that initially belong to group -1. Since this involves iterating through all n items, it takes n time. Next, we build the adjacency lists and in-degree arrays for both the item graph and the group graph. For this, we process the dependencies provided in the before items array. Let's denote the total number of dependencies as E. Each dependency is processed once, so building the graphs takes E time. After that, we perform a topological sort on the groups. With m groups in total, where each group could potentially depend on every other group, the group graph has at most m2 edges in the worst case. Using Kahn's algorithm for topological sorting, we process each node and edge exactly once, leading to a time complexity of m plus m squared for this step. Now, we move to the topological sort for items. Similar to the group graph, the item graph consists of n nodes and e edges. Using the same topological sort logic, this step requires n plus e time. Once we have the sorted order of items, we organize them by their respective groups. This involves iterating through all n items, which takes n time. Finally, we iterate through the sorted group order and append the items from each group to the result, which is another n operation. When we combine all these steps, the total time complexity becomes n plus e plus m plus m squared plus n plus e plus n. Simplifying this expression gives us n plus e plus m squared. In the worst case, the total dependencies E can go up to n-2, and the group dependencies m-2 can also reach n-2 if every group is unique and depends on all others. Therefore, the worst-case time complexity is n squared. To analyze the space complexity, we look at the memory requirements for each component of the algorithm. First, the adjacency lists for the item graph and group graph store all edges, requiring e space. The in-degree arrays for items and groups require n and m space, respectively. During the topological sorting process, we use a queue, which can hold up to n items or m groups at any given time, adding another max n m space requirement. Additionally, the group _to_ items dictionary maps items to their respective groups, which requires n space. Finally, the result list stores the final sorted order of all n items, contributing another n to the space complexity. When we sum up all the components, the total space complexity becomes e plus n plus m plus max n m plus n. Simplifying this expression gives us n plus e. In the worst case, where the total dependencies E reach n-2, the space complexity becomes n squared. Comparing this optimized approach to a brute force solution highlights the efficiency of our algorithm. A naive method would involve generating all permutations of items and checking if each satisfies the dependencies, leading to an infeasible time complexity of O(n)(n plus e). By leveraging graph-based topological sorting, we reduce the time complexity to O(n plus e plus m squared, making the algorithm much more practical for larger inputs. We can summarize the time complexity of the algorithm across different scenarios to better understand its performance. In the best case, where there are no dependencies, e equals 0, and all items belong to the same group, m equals 1, the algorithm runs in O(n) time. In the average case, with moderate values for e and m, the time complexity is dominated by O(n plus e). Finally, in the worst case, where e equals n(2) and m equals n, the time complexity reaches O(n squared). To back this up, we can mathematically prove the bounds of the algorithm. Each node and edge in the graphs is processed exactly once during construction and topological sorting, ensuring linear scaling. The sorting of groups adds an O(m squared) overhead at most, which is dominated by O(n squared) in the worst case. Overall, this optimized approach efficiently handles the problem constraints, reducing the complexity from exponential to quadratic, making it suitable for large-scale inputs. One common mistake in this problem is confusing intergroup and intragroup dependencies. Intergroup dependencies define the order between entire groups, while intragroup dependencies deal with the order of items within the same group. Failing to differentiate between the two can result in an incorrect graph structure, leading to cycles or invalid outputs. To avoid this, it's crucial to construct two distinct graphs, one that captures the dependencies between groups and another that handles the relationships among items within each group. Another issue arises with isolated items, those that do not belong to any group, typically denoted by group -1. These items are often overlooked, but they must be treated as part of their own virtual group and included in the topological sort process to ensure your solution is complete. Additionally, improper cycle detection during topological sorting can cause infinite loops or logical errors. To handle this, make sure your DFS implementation correctly tracks nodes as visited, visiting, or unvisited. Lastly, inefficient graph construction can lead to poor performance, especially with larger inputs. Representing dependencies using adjacency lists and avoiding unnecessary nested loops can significantly optimize your solution. Edge cases are another area that often trips up developers. Scenarios like having no dependencies at all items belonging to the same group, or a graph that is completely disconnected should be thoroughly tested to ensure your solution is robust. Failing to account for these can cause your implementation to break in unexpected ways. From an interview perspective, this problem is an excellent way to assess your understanding of key algorithms like topological sorting and graph traversal. It's important to demonstrate how you can break the problem into smaller, manageable subproblems, such as separating intergroup and intragroup constraints. The optimal approach here involves building two separate graphs, one at the group level and another at the item level, performing a topological sort on both, and then combining the results. This method is not only efficient but also easier to debug and explain. Furthermore, be prepared to discuss the trade-offs of your approach. For example, why a graph-based method is ideal for this scenario and how it balances clarity and performance. Interviewers often focus on how well you can justify your design choices and whether your thought process is clear and logical. If you're preparing for this problem, it's helpful to look at related problems that build on similar concepts. For instance, LeetCode 207, Course Schedule, is a foundational problem that focuses on detecting cycles and performing a topological sort to determine whether a set of courses can be completed. LeetCode 210, Course Schedule 2, extends this idea by requiring you to produce a valid order of courses based on their dependencies. Another interesting problem is LeetCode 269, Alien Dictionary, which uses topological sorting to determine the order of characters in an alien language based on given constraints. Finally, LeetCode 444, Sequence Reconstruction, is a more challenging variation that involves not only topological sorting but also verifying if a unique ordering exists. Exploring these problems can deepen your understanding of the patterns and techniques that are central to solving graph-based dependency challenges. While the standard approach for this problem involves topological sorting with two graphs, there are alternative methods worth considering. A DFS-based topological sort is one option, but it can become harder to manage when you have to deal with both intergroup and intragroup constraints. It's also generally less intuitive to debug compared to a BFS-based approach. Another alternative is to use union find to dynamically group items. This can simplify some aspects of managing groups, but it often becomes cumbersome when incorporating dependency relationships, making it less practical for this specific problem. Finally, some solutions use a priority queue with Kahn's algorithm to handle topological sorting. This can be particularly useful for tie-breaking scenarios where lexicographical order matters. However, in this problem, adding such complexity may not be necessary and could complicate your implementation. It's important to weigh these alternatives carefully and choose the one that best aligns with the problem requirements and constraints. Great job! We've successfully tackled LeetCode problem number 1203 by leveraging topological sorting for group and item dependencies. This problem demonstrates the power of graph algorithms in solving real-world scheduling and dependency challenges. Make sure to practice similar problems to solidify your understanding. Thank you for watching, and don't forget to like, share, and subscribe for more content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!